Dear friends, back to Calculus Minis. Today we are going to talk about something called the differential. The differential is a term you have heard. You have heard terms like derivative, the differential, and I can tell you that most of you are mixed up. Most of you possibly are not very clear of what the term differential is and what really is the difference between derivative and differential and all these stuffs. Because a lot of things are done in quite an hand waving way in calculus so that you don't much get an idea of what's going on. So we have all heard about it, but we want to know what it is. Derivative is nothing but you take the ratio of the change in y by change in x. So if how much has the function value changed if the x value has changed. So if y equal to fx is a function, and if I take this function y equal to fx, which I have already done here. So if my x value is changing, then what is my change in y value? I take the ratio and I make the change in x value come close and close to 0, and then whatever is the value of the ratio, it doesn't matter, and if that is called the derivative, if both from the left side and the right side the limit are equal. That is what you know. So you can understand here what I mean by the change of x. So if I add some little quantity delta x, which could be positive or negative, then this delta x, so the new value of x is x plus delta x. So if it is a positive thing, you go to the right side of x. If it is a negative thing, you go to the left side of x. And then when f is value of x is x plus delta x, the value of the function is f of x plus delta x. And the earlier value was fx, so the change in the y value is delta y, which is f of x plus delta x minus fx. So you can understand this. This is not a big deal at all to understand. So now I have tried to look into the YouTube and many books, trying to some of the standard calculus books which are found in most Indian colleges and cities and taught in most schools, especially in our small towns. It should be important that small town people do have a right to get a good mathematical education, because I strongly believe that people can understand things. So when I was also a student, this term differential came in. So somebody said, okay, when delta y, the change in y is very small, I will call it the differential of y, because somebody called Leibniz, the great man, who also was a co-discoverer of calculus along with Newton, independently of course. And on the type of things or the symbols or the type of calculations that we do in calculus today is really due to Leibniz. Its root lies in Leibniz's approach rather than in Newton's, because Newton was more geometric. If delta x is small, we will call it dx. So when I wrote the differential of a function, I wrote in YouTube. I looked at the first video. Exactly that was what they were writing. And so we call dy the differential of y and dx the differential of x. This game is over because delta y and delta x more or less the same. Now you know that the derivative is nothing but limit of delta y by delta x as delta x goes to 0. So at the same time, we always say that dy dx equal to f dash x. This is our way of saying it, and this has been there for hundreds of years. People have been saying it. But I was told in my college and even in my school days, in my high school days, never think that dy by dx is the ratio of the quantities dy by dx, because dy is actually del y, dx is actually del x. You have to have the limit of those ratios to get f dash x. So here it is a symbol. Here the symbolical meaning dy by dx actually means ddx is acting on the function y or function f to give me f dash x. And I was told never think that f dash x is the ratio of dy and dx, the differentials. Yes. But I was very curious because, come on man, it looks like you have taken a ratio of something. And people also said and also wrote dy is equal to f dash x dx. In many calculations these things were written. So this is very ambiguous. In one hand you are telling that dy by dx, you cannot think of f dash x as the ratio of dy by dx. But you are also writing dy is f dash x dx. What does it mean? This is too much confusing, isn't it? If you agree with me, then you can comment back and tell me. And if you don't agree, then also comment back and tell me. Mathematics is all about discussion, learning through discussion. Then I was saved by a book written by a very famous mathematician Courant and another famous mathematician John, Fridge John actually his full name, very famous in functional analysis, who worked in the Courant Institute of Mathematics of New York University. And Fridge John is also famous in my subject optimization for his Fridge John optimality conditions. Now, there's a book called Introduction to Calculus and Analysis. There are two volumes, volume 1 and volume 2. So, I'll do two book sessions, one on real analysis and one on calculus. They will appear in the same day, one after another. And then you will see, I'll pick up some of my best books of calculus and real analysis and we will discuss it. So, I'll definitely discuss this book. So, let us look at the definition of the derivative once again. What does the derivative say? The derivative is nothing but the limit of the change in y, which is the top part f of x plus delta x minus fx divided by delta x. How much y changes with unit change of y? If I change delta x is equal to 1, with unit change, then the change in x f is, or change in the function value is f of x plus 1 minus fx. That's all. So when the change is delta x, this is a unitary method. So when the change is delta x, then the change is f of x plus delta x by fx by delta x. That's it. So the relative change, right? Or if you think of delta x as time and f is the distance traveled, then you are essentially telling that basically I'm covering, this is nothing. When you write when you fix x and take a delta x minus f of x by delta x, you are writing the average velocity of the car, for example, the car or a particle traveling between x to x plus, traveling between f of x plus delta x to f of x in the time period delta x. That's all. Now, f dash x is something. So now if you observe, since x is fixed, delta x is actually the variable here. So this is a ratio of two functions of delta x. The whole thing is a function of delta x. While f dash x is independent of delta x because you actually operate the limit here. So you can take f dash x to the right hand side and then bring the whole thing inside, f dash x inside, because if you apply the limit on f dash x, it will remain unchanged. So you do a little manipulation and write something like this. So what you have, that limit of delta x going to 0, f of x plus delta x minus fx minus f dash x delta x divided by delta x is equal to 0, which means the quantity which is in the numerator, that is this big quantity, this lambda quantity, f of x plus delta x minus fx minus f dash x into delta x, if this is once this is divided by delta x and as delta x goes to 0, if this becomes 0, then it must mean that f of x plus delta x minus fx minus f dash x delta x is going to 0 much faster than delta x or x. Or if it didn't happen, delta x would go, delta x went faster, then this would explode. This will go to infinity possibly. So because it is going to 0 means the numerator must be going to 0 much faster than delta x. So such quantities of the numerator which when divided by delta x and then the limit of delta x is taken as delta x goes to 0, limit as delta x tends to 0 is taken, gives me 0, then the top quantity, this quantity, is called an O of x quantity, small o of x, small o. Okay. Now what happens is I can now write, so f of x plus delta x minus fx minus f dash x delta x is O of delta x. So that's what I write. So it's kind of an error basically. It tells you that f of x plus delta x minus fx is actually equal to f dash x into delta x, but actually that's not true because there is a limit thing here. So there must be some error. So what does it tells me? Tells me that if you move a little away from x, I can write, find the value of f of, approximate the value of f of x plus delta x using the linear function fx plus f dash x into delta x. So essentially this is the equation of the tangent at x fx. So we will not get into that. So now this you know is as delta y, this part. So delta y is f dash x into delta x plus O of delta x. So this small O of x is the error part. So when delta x goes to 0, this goes to 0 much faster than delta x. It just bloops comparatively. Now, Courant and John made a definition, and this is a definition. Please understand, this is a definition. Now you can say, why are you calling it a definition? Don't challenge it a definition. Let us see. I'll give you a historical link as to why this is the definition. You will see in the next calculus minis this will come as why the following definition has been chosen by Courant and John. And I'll go back to Leibniz and his fantasies. Courant and John defined dy, the differential of, not y, x. So differential of y is dy, and that dy he defined as f dash x. So this portion is defined as d of y, differential of y. So delta of y, the change in y is the differential of y plus some error. So let us look at it in a different. Now consider I take the particular function y is equal to fx, and that fx is equal to x. The line through the origin at angle 45, making of angle 45 degree with the x-axis. So by definition, the differential of y is same as differential of x because dy is equal to dx. But what is the differential of y? That is f dash x into delta x. But from this definition. But what is f dash x here? Because y is equal to x. F dash x is equal to 1. So dx is exactly equal to delta x. So it is absolutely fair to write that dy is equal to f dash delta x. So the differential of x is nothing but delta x. Differential of x. Now, so it's absolutely fair to write dy is equal to f dash delta x, which you have seen in your calculus courses, and f dash x is actually the ratio of differentials. Let us look at this problem geometrically. So once you look at it geometrically, things would be much clearer. So let us look at it geometrically. So let us take this function fx. This is the graph of y equal to fx. Graph, in short graph I wrote, graph of y equal to fx. Okay. Now this is the point x. So this point here on the graph is your point with coordinates x and fx, right? Now you draw a tangent at that point, making an angle theta with the x-axis. So the slope of the tangent tan theta is the derivative of f at x. Now what you do, you take a new point x plus del x. So this is your del x. I've taken del x to be positive here. Doesn't matter. You can take it on the other side also. So now if you look at what is the value of f of del x, look at the point P. The point P here has the coordinate x plus del x and f of x plus del x. Right. Now if you look at y, this point, if I call this point as x, the point x I mark as A and the point x plus delta x I mark at B, then the AB, the length of AB is del x and OB is actually y. So we draw the triangle here, the perpendicular, this triangle that you see. This is theta. So let this tangent cuts this line joining the point P x fx with x plus del x. So let that be cut at t. This point is t, right? This is t. So f of x plus del x is y, that is OB, plus OT plus PT, right? So y plus delta y is my f of x plus delta x. So y plus delta y, as you have already seen earlier. So y plus delta y is exactly equal to this, and this is exactly equal to this. So y plus delta y is your f of x plus del x, right? So now what is your delta y? So what is y? Y is OB. So delta y is OP. So delta y is OP, and OP is nothing but OT plus PT. So PT is your error. So what is this tan theta? If you go by corresponding angles, this is also theta. This angle is theta. So OT by del x is tan theta, which is f dash x. Okay. Now, so by definition, what we had, OT is actually del y, and PT is actually O of del x, that error, the small o. Because you see, if I make del x go towards 0, that is, if I move towards x from this direction, the if I move del x this much, this has considerably reduced. See, I am quite far from x. As I am moving my del x, I am quite far from x. But observe that my value of this difference, O of delta x, this value has actually decreased much faster than x has decreased and come towards x. It is going much faster towards 0. That's the meaning. So now that is O of delta x. So this part is your OT is actually is your dy. So that's the geometrical meaning of the differential. Now, obviously, you can understand when I have the line y equal to fx, then it has a constant angle theta equal to pi by 4. Now, if you take another point x plus del x and take this point y plus del y here, you can understand this angle is 90 degrees and this is pi by 4, a corresponding angle. So, this is also pi by 4 because this will be 45, this will be 45 and this will be 90. So, this is equal to this. So, del y is equal to del x. But del y here is same as f dash x del x. So del y is equal to dy. And dy is equal to del x. And what is f dash x? Is the tan of pi by 4, which is nothing but 1. So dy equal to dy equal to delta x equal to dx. You can write it equal to dx. So dx is equal to delta x. And that's it. So now this whole operation, so when y is equal to x, basically delta y and delta x is the same. Dx is the same. Basically your O of delta x is not there, is 0 in this linear case, straight line case. So you see, now you have a concrete meaning of the differential. Actually then this is actually your dx. So your derivative is nothing but the slope dy by dx is equal to tan theta, which is exactly equal to the derivative. So derivative is actually the ratio of differentials when the differential is defined in this manner. We will tell you the Leibniz story in the next calculus minis, and that will be fun. You will know that what a deep insight they had. They might not have been very, very rigorous like what we are now doing, but they had a huge insight. And it's very important to understand this insight. Sometimes doing these intuitive jumps like physicists gives you a lot of kick and a lot of fun in doing mathematics. I bet you that physicists actually have a lot of fun. They can see a lot of things very early, and then mathematicians come and actually develop the rigor. And that is how these two subjects go in tandem. If you never say that, okay, I would like to look at mathematics completely in isolation, you can, but that won't be much fun unless you see how a lot of things go together, how science and industry advances with mathematics, which is a slogan for the Society of Industrial and Applied Mathematics. So, with this, let me end my story today, and We will get along, and maybe after this, I'll have some more fun videos, and then we'll get on to the technicalities. So, thank you, good night, nice weekend.